Welcome students to this fourth part of lecture 1, and in this part we are going to talk about the Fourier series for a function with arbitrary period. So up till now what did we learn? If we recall, if f is 2 pi periodic function, right, and which will be defined between minus pi and pi, then you can write f of x as a naught plus sum an cosine nx plus bn sin x, where an's and bn's are the Fourier coefficients, which is given by 2. This is what we learned, right? Now the point is this: not always can we get a function which will be 2 pi periodic. Yes. So what do you do in such cases? So what we essentially do is this. See, first of all, let's start with this. So assume, so this is given to us. Assume f is k periodic, or maybe let me put it maybe p periodic. Let me put it p periodic, and p we are going to assume it to be equals to 2l. Yes, of course p is positive number and we are going to assume it to be 2 times l. Okay, where l is of course positive again, periodic. Yes, periodic. So this is what we are assuming. Yes, so basically it is giving it to be periodic, which we are going to write it as 2l periodic. Clear? Okay. Now the point is this. See, essentially we know how to deal with functions which are of 2 pi period, right? So how do you work with a function f which is 2l periodic? Yes. So basically for now we just assume it is to be 2l periodic, and then we will use our earlier knowledge for this. So let's see what we do. Now you see, what we do is we set this new variable. We set this new variable. This variable is given by this. So v is our new variable. Okay, and this variable, so initially let's say f of x will be defined, right? F of x is given to us. So this f of x is given to us. Yes. So we'll use that x. Yes. So essentially v we are going to define it to be pi by l times x. Okay, and also we define a new function g of v to be as f of x. Okay, see, f is given to us, right? So basically f of x is a 2l periodic function that's given. So essentially here it is given that f of x is 2l periodic, right? That's what it means. So this is given to us. We know what f is, right? Now we are defining a new function g such that g of v equals to f of x. And what is v? V we are defining it to be pi by capital L times x. Of course L is positive, we know that, right? Yeah. So this is, all of this is defined, and then so essentially what is x here? X is L by pi times v, right? L by pi times v, right? So you see, now f is given to be 2l periodic, right? So f of l and f of minus l are going to be same, right? Okay, so we are assuming that it is 2 pi periodic in, let's say, minus pi and pi. Yes, so that's not a problem, so we can assume that. So what we are going to do is this. See here, if we do that, since it is 2l periodic, g will be 2 pi periodic, because you see g of, if you do it, g of, let's say, pi, yeah, is f of l by pi times pi, which is f of l. Okay, and again g of, if you look at minus pi, this is going to be again f of minus l. Okay, now you see, since f is 2l periodic, without loss of generality we can assume, so 2l periodic, that is, we will assume that f of l equals to f of minus l. So that's what we are trying to do it. I mean, we'll fix, we'll just set our problem like that. Okay, since it is 2l periodic, this is true. So in this case you do realize that g will be 2 pi periodic, and that will imply g is 2 pi periodic. Clear? So you understood what happening. You see, f is given to us and it is given as 2l periodic function. So essentially we can assume that f of l and f of minus l are basically the same functions. Yes. Okay. So now you see if you set v to be pi by L times x, this particular variable, then g of v will be defined as f of, and we define g of v as f of x. If we define something like this, so this is the definition, this is definition, again this is definition. Okay, so if we define it like this, you can see that g is going to be 2 pi periodic. Now for 2 pi periodic functions, we know what happens to the Fourier series, so we are going to use that idea. Okay, so you see g of v, right, which is essentially f of L pi by v, right, that's our definition. Yes, and that will be, we can write it as a naught plus summation n equals to 1 to infinity an cosine nv plus bn sin nv, right. And of course here all of that, so where, let me put it this way, a naught is 1 by 2 pi minus pi to pi f of, let me write it this way, otherwise you may get confused. This is the notation which we are going to use. So essentially you see it is, now this is our new variable, right, this is our new variable. See, g can be written like this. So AC, if we want to write it in terms of f, here we should write it as g, right, but g of v is f, so we write it like this, and ans are 1 by pi minus pi to pi f of L pi by v, clear, and then cosine nv dv. Yes, and bn you have to define it like 1 by pi minus pi to pi. See, this is g of v, right, which is f L by pi times v, and then you have sine of nv. Clear? You remember, it will be g of v sine of nv, right? So that is this. So this holds for all n greater than equal 1. Okay, right. So this is the thing which we are going to get for an arbitrary period. Now we wanted to, simplify bit. So what we do is this. See, since v is pi by L x, so dv is pi by L dx, right? See, dv is pi by L dx. If you can do it like this, dx, yes. So we will replace this as substitution and substitute it in our inequality. So if you do that, you can write it like this. See, f of x, yes. So I am just skipping one line and I am just writing it like this. So L pi by v, you see L pi by v is x. So f of x can be written here. I am just substituting that variable, right? And let me write it this way. This will be 1 by, so it will be a naught plus sum n equals to 1 to infinity, and then you have an cosine n pi by L x plus bn sine n pi by L x. Is it okay? And this holds again for all n greater than equal 1. Okay, and what are the Fourier coefficients? Where a naught is 1 by 2L minus L to L f of x dx. Yes, okay. Let me do this part, yes, so that you may it is not a big issue for you. See, from here what is a naught? 1 by 2 pi minus pi to pi f of L by pi v dv, right? So you see a naught is 1 by 2 pi minus pi to pi f of L by pi v dv, right? And you remember your variable is v equals to pi by L x, right? And v equals to pi by L times x. So what is dv? It is pi by L times dx. So if you replace it here, you see it becomes 1 by 2 pi, and then your this integral minus pi. So when v is minus pi, L is minus x. So it is becomes L to minus L to L, and then this f, it becomes f of x, right? And then this dv becomes pi by L times dx. So you see this pi and pi gets cancelled out, so it becomes 1 by 2L minus L to L f of x dx. And similarly for the other a naught and an and bn, you can actually do it. So that is for you to do. So please do it yourself. This is 1 by L again minus L to L f of x cosine in pi x by L dx. Okay, and bn will be given by 1 by L minus L to L f of x sine of n pi x by L dx. Is it okay? So this holds for all n greater than equal 1. Yeah. So I hope you can do it yourself. Please do it yourself. Check it. Check this part. Yes. So I hope this is clear now. Right. So now what we are going to do is essentially look at one particular problem of how to do exercises using this Fourier series formula. Okay. Right. So let's do this. I am going to remove this part here. It's a distraction actually. Let's remove this part, and then the exercise which I am going to do, first exercise, is called the periodic rectangular wave. Okay. So this is called the rectangular wave. Very, very important example. Rectangular wave. Okay. So what it is a special kind of function. Yes. So let's say the function is given like this. F of x is essentially a constant. Yes, minus some k. Yeah, some constant, and it is given by minus pi x and 0. And again this constant, another constant between 0, x and pi. Clear? And it is also given that f of x plus 2 pi equals to f of x. Okay. So you do realize from this particular formula, this holds for all x in R, you do realize that f is 2 pi periodic. Yes. So see, the thing will look like this. Between, so let's say this is minus pi, this is pi, and then between 0 and pi it is k. Let's say this is k. I'm just putting some value. It doesn't really matter what k is. K can be 1, 2, whatever. Yeah. And between minus pi to 0 is minus k. So let's say minus k is somewhere here. So it is minus k. Okay. It will look like this. Yes. And so you understand that it will go on doing this thing. So in the other part it will do this and do this. Yes. So it will go on doing all these things. Okay. So this is a periodic function. See, if you do realize that periodic function doesn't have to be defined in all of R. It is defined only in some periodic and period, which is in this case is given by minus pi and pi, and then you can just expand that whole thing down, right? Now one thing also you have to understand that this f is not defined at 0. Why it is not defined at 0? Because essentially you see 1 point in this case is not a huge issue. Yes. In this case we will define f of x to be undefined at 0 and plus minus pi. Yeah, we'll just keep it like this, so we don't have to worry about it. See, essentially if you want to write it in terms of Fourier series, the Fourier coefficients comes out to be as integrals, and integrals at a finite number of points does not really matter. Yes, so it does not really matter. Yeah, so we are going to keep it here undefined. So let me put it this way: f is undefined at 0 and plus minus pi. Yeah. Yes, you do realize what's happening, because to find the Fourier coefficients, the value of function at a finite number of points does not matter because of the integral thing. Yes. Okay. So let's do this. So let's find the Fourier series of this. So first thing first, you do realize that the Fourier series exists for this. Why? Because this is basically a piecewise continuous function, right? Okay. So in minus pi and pi, right? It's a piecewise continuous function between minus pi and pi. 0 is the only problem here. Yes. Okay. So first of all, let's just find out what a naught is. So a naught in our case is 1 by pi, right? 1 by 2 pi minus pi to pi. So in this case we have to break it, minus pi to 0, f of x dx, right? F of x is minus k dx. Yes. And then again 1 by 2 pi, again the other part is 0 to pi, right? And then you have k dx. Yes. you do see that this will be from here, if you calculate, it will be k pi, okay, minus k pi, and from here it will be k pi. So let me do it this way. Yeah, it will be k minus k by 2, so it will be minus k by 2, and then this will be k by 2, right? This is a very simple calculation, that is going to give me 0. Yes, so a naught is going to be 0, so there is no first coefficient. Yes, right. So let's look at what ans are. So ans, this is, you know, as it 1 by pi minus pi to pi f of x cosine nx dx, right? Cosine nx dx. Yes, okay, so it will be 1 by pi minus pi to 0. Yes, f of x is minus k in this interval, and then you have cosine nx dx here, and then plus 0 to pi, and then this is k sine nx dx. Is it okay? I hope this is clear. Okay, and then you will put it in a bracket. So this holds for all n greater than equal 1. Yeah, let me put it this way. So you can see that essentially I want to calculate, try to make an integral of minus pi to pi cosine nx and minus 0 to pi sine nx. That's going to be 0. Yeah, this is very, very easy to check. So this is going to be 0. So please check it yourself. Check it yourself. This is very easy, right? Yourself. Okay. So I'm not doing that part. Yeah. So this holds for all n greater than. So an coefficients are basically all 0. What about bn's? Are they 0? Unlikely, right? That should not work. Otherwise, the whole Fourier the series becomes 0, right? Okay. So 1 by pi. This is, you remember, it is f of x sine nx dx, right? Sine nx dx. Okay. So if you want to write it, it becomes 1 by pi minus pi to 0, and then minus k times sine nx dx plus, let me put it in a bracket, 1 by, and then you have integral 0 to pi, right? 0 to pi k times sine nx dx. Yeah, I hope this is correct. I am not making any mistakes here. No, this is okay, right? Okay. So now you see, the thing is, let's do this. So this becomes, see, minus pi to 0 minus k, this particular thing, yeah, if you want to write it, it becomes then 1 by pi, this minus this, right? So this one minus this one, this becomes 1 by pi, and then k times sine nx, so that will be cosine nx, right? Cosine nx by n, and then I have to indicate, evaluate it between minus pi to 0, and then minus k, and then I have cosine nx by n again, and then I have to evaluate it between 0 and pi. Okay, if I do that, what I am going to do is, you are going to get cosine 1 by n and cosine minus pi by n, so that will be minus 1. Okay, so bn's, we are going to get it as k I am going to take common by n pi, okay, because that n part is there in common in both. K and k by n is common in both the terms, so I am just taking it out, so it becomes k by n pi, and then I have cosine 0, yeah, and cosine minus n pi, and then cosine n pi, right? So that it becomes cosine 0 minus cosine minus n pi minus cosine n pi plus cosine 0. So when you do these calculations, please do it carefully, otherwise there is a chance of making a mistake here. Yeah, so it becomes 2k by n pi 1 minus cosine n pi. Yeah, very simple. Yes. So you see, depending on whether n is positive or negative, it becomes, this becomes 1 or minus 1, right? Okay. So essentially what happens is, let me put it this way, b1, yeah, b1 in this case will be 4k by n, pi, 4k by pi, yeah, and B2 will be n equals n is even in this case, so if we just put it there, it becomes 0. See, it will be cosine 2 pi, right, which is going to be 1, and then 1 minus 1 is 0. So basically all the even terms are going to be 0, and odd terms are going to get some values. So it becomes 4k by 3 pi, clear? And then B4 is again going to be 0, and then B5 is going to be, of course you don't have to write everything, but for now I'm just writing one to a few terms, but you can go on, right? And you do realize that that will give you a series. So let me write down what the series is. So in this case, the series becomes, so the Fourier series of f, Fourier series of f of x is given by 4k by pi, right? 4k by pi, right? Yeah. And then sin x, b1 times sin x, b2 times sin 2x, b2 is 0. Then we have sin 3x, right? Sin 3x is, you see, 4k by 3 pi. Yeah. So it is 1 by 3 sin 3x plus 1 by 5 sin 5x, plus it goes on like this, right? So this is the representation of this particular rectangular wave function. Yeah. And one beautiful thing about this is, see, at the point, let's say this function, yes, see, this function is continuous everywhere in minus pi except at point 0, right? So let's say at the point pi by 2 here, yeah, the function is continuous. So if you remember the convergence theorem we did, the convergence theorem guarantees that the sum of the series is going to be f at that point, right, if the point is a point of continuity. So in this case, pi by 2 is a point of continuity of f, right? See, f is continuous at the point pi by 2. So essentially f of pi by 2 will be equals to the sum of the series. So therefore, let's say we can say, therefore f of pi by 2, and what is f of pi by 2? It is essentially f of pi by 2, let's say, I'm just assuming one point pi by 2, it's nothing special, I just wanted to show you something, right? So that will be equals to k, it's a positive number, right? K, you see, pi by 2, f is k, right? Okay, so this is what we are assuming, and it's a point of continuity. See, this is a point of continuity. Yeah. So what does Fourier convergence theorem says? It says that since it is the point of continuity, it is actually equals to the sum of this series. This series of course converges and it is equals to the sum. Clear? So what is the sum of the series? It becomes 4k by pi, and then it becomes sine of pi by 2, yeah, which is 1 minus sine 1/3 times sine of 3 pi by 2. So it goes on, you understand, it becomes minus 1, and then the next term is sine of 5 pi by 2, which becomes 1, so that is plus 1 by 5, and then it goes on like this. So this will actually give you this thing, that 1 minus 1 by 3 plus 1 by 5 minus 1 by 7. This series, the sum is given by pi by 4. See, the sum, the series converges of course, and then you can actually say that this is positive, so it gets cancelled, it becomes pi by 4. Okay. So you do realize that Fourier series can also be used to calculate the sum of series. So with this I am going to end this video.